Alrighty, in this video we're learning about linear transformations. Now, linearity ends up being a very general topic that's extremely powerful, but for now we're just going to learn how to check if something is linear or not. So it turns out a lot of things that are useful are linear, and basically when you get to maths in uni, you're studying linear algebra, and that's sort of the main topic you'll do. But let's talk about checking these. So essentially what you need to do is check the first two properties there, property 1 and property 2. So that if you add two inputs, that's the same as doing each one and adding the outputs. Or if you times the input by a number, that's the same as timesing the output by that same number. So if those two things are true, then we have a linear transformation. So let's check that this thing here is a linear transformation. So we're going to check the first property, which is that t of a vector u plus a vector v has to be the same as doing t of the vector u and then adding on t of the vector v. Those two things have to match. So let's set u to be the vector, we'll call it x1 and y1. And we'll set v to be the vector that we'll call x2 and y2. So what we need to do is look at t of u plus v. So we'll just step out what this actually means. Try not to get thrown off by the notation. You literally just step through and do exactly what it says to do. So what is u? U is x1 and y1. And what is v? V is x2 and y2. And we're going to do t to this. But before we do t to this, we have to simplify the inside. So that vector just becomes x1 plus x2 and y1 plus y2 on the inside. Now, if we do t to something, what you do is to get the first component of your answer, that's literally the same as the second thing of what you put in. So we're going to take the bottom value, y1 plus y2. That is what goes on the top. It's really weird, but that's how t works. Now, to get the bottom value of t, you need to take the two things that you put in, and you need to add those together to get the bottom value. So the bottom value of t is going to be the first thing, x1 plus x2, plus the bottom thing, y1 plus y2. So now, what we've done is we've worked out t of u plus v. Seems very weird, but that, by definition, is what t does. Next thing we need to work out is t of u plus t of v. And what this means is t of u is x1, x2, x1, y1. And v is x2, y2. So let's just see what t does. T is this transformation. It takes, to get the top entry, you have to get the bottom thing and move it up. So let's look at what we're going to get here. The bottom thing is y1 here, that goes up the top. Next time, the bottom thing is y2, that goes up the top. Now, to get the thing on the bottom, it ends up being those two things added together to get the bottom thing. So those two things are x1 and y1. And then on this one, they're x2 and y2. Very weird. But that's the definition of what t does. So this ends up being, if we write it as one big vector, y1 plus y2, and then x1 plus y1 plus x2 plus y2. And just to make it look like the other one, I'm going to rewrite the bottom. So I get y1 plus y2, and I'm going to get x1 plus x2 plus y1 plus y2. And these two things match. So that is really good. So the first thing was t of u plus v. And we've just shown that that equals t of u plus t of v. So that is wonderful. We've checked that the first bit of the linear transformation is true. The next thing that we need to do is show that t of k times u is the same as k times t of u. We need to make sure that works as well. So let's check it. We're going to keep u as our same vector from before. That's x1, y1. We'll just keep k as k. So t of ku is going to be t of k times x1, y1, which is t of kx1, ky1, which is, let's see, what does t do? T moved the bottom one up the top, so we're going to get ky1 up the top, and to get the bottom one, we're going to add the two values. That's what t does in this case. Next, what we're going to do is we're going to look at k of t of u. So that's going to be k times, yeah, this is going to be t of x1, y1. What does t do? Well, it moves the bottom one up the top, and to get the bottom element, you just add the two elements together. And now let's pull the k in, so we're going to get ky1 and kx1 plus y1. And then if we expand out that bottom bit, we get ky1, kx1 plus ky1, and that is exactly what we need. So that's really good news. It turns out that t of ku definitely is the same as k of tu. Therefore, t is a linear transformation as both conditions are satisfied. All right, now I'm going to show you a simpler example next. It's just a normal function that we're used to dealing with. We want to show this is a linear transformation. So we should have the f of u plus v is the same as f of u plus f of v. And we also want the f of ku is going to be the same as k of fu. So let's see if that's true. So u and v are just going to be real numbers in this case. This is not a vector function, this is just a normal function. So f of u plus v is going to be 3 times whatever I put in, u plus v, which is going to be 3u plus 3v. And also f of u plus f of v is going to be 3u plus 3v. Oh my goodness, they're the same. So this first condition is true. Now to get my next condition, what we've got to look at is f of ku is going to be 3 times ku, which is, we'll write it as k. I'm happy to leave it like that actually. And then k of fu is going to be k of 3x. K of 3u, which is going to be 3ku again. So yep, this second condition is true. Therefore, f is a linear function. All right. You could have a function almost like f of x equals x squared. This is a quadratic. I might call it g actually. And I can immediately show by a counterexample that this is not a linear function. So if we, if we look at this, I could try doing g of 1 plus 2 versus g of 1 plus g of 2, and we'll see that this does not work. So g of 1 plus 2 is the same as g of 3, and then that's going to be 3 squared, which is 9. G of 1 plus g of 2, so that's going to be 1 squared plus 2 squared, which is 1 plus 4, which is 5. So these do not match. Therefore, g is not linear. It fails that first test. And we'll do an example of a vector function that's not linear. So I'm going to pick u to be the vector 1, 1, and v to be the vector 2, 3, and we'll show that this is not a linear transformation. Okay, so let's do this. T of u plus v is going to be t of 1, 1 plus 2, 3, just like that, which is going to be t of 3, 4. Now, what does t do? T leaves x where it is, so we're still going to get 3 on the top. And on the bottom, y is going to go to y squared, so we're going to get 16, because that's 4 squared. So that is t of u plus v. Now, let's check out t of u plus t of v. That's going to be, let's see. So that's going to be t of 1, 1 plus t of 2, 3. So that's going to be, let's see, what does t do? It leaves 1 and it puts the squared on the bottom, and 2 and it puts 3 squared on the bottom. So that's going to be 1, 1 plus 2, 9, which if we put that into a single vector, that is 3, 10. So we can, that's a 16, not a 10 on the left there as well. So we can see that the top numbers do match, but the bottom numbers do not match. Therefore, t of u plus v does not equal t of u plus t of v. Therefore, t is not linear because it failed that first test.